The demand for fluid simulation and rendering in virtual reality is increasing. To achieve higher visual quality in near-eye rendering within the VR simulation domain, we propose a novel visual perception-driven fluid rendering method, ViP-Fluid, which further enhances VR fluid's rendering quality while balancing efficiency. Many spatial and temporal fluid phenomena, such as splashes, ripples, fragmentation, turbulence, vortices, and water crowns, attract visual attention during simulation and rendering. In VR near-eye rendering tasks, improving the quality of these visual interest areas while balancing the efficiency in laminar or hidden areas is a valuable direction to explore. Our method starts by taking the physical states of the particle system from the previous frame and the gaze information from VR users as inputs. Next, it employs a spatiotemporal saliency model for multigranularity simulation and rendering of Lagrangian fluid systems. Features from both spatial and temporal domains are weighted and combined into a saliency measure to guide subsequent updates in particle granularity. After undergoing updates through splitting and merging, as well as organizing multilevel particle memory fragments, these particles are fed into the solver to compute their states for the new frame. To minimize temporal jitter in the physical simulation process and ensure smoother and more stable visual outputs, we introduce a temporal acceleration strategy. This involves skipping detailed computations for less significant particles and instead sampling from the spatiotemporal neighborhood's velocity field. We propose a PTPE model, which is used to guide the timing for updating particles and activating the acceleration strategy. Finally, the computed particles are rendered using the screen space fluids algorithm, displayed on a near-eye device, and continuously looped to simulate dynamic fluid behavior. Slow rendering or large fluctuations in fluid dynamics can deteriorate the visual perception experience for users due to the unsmooth nature of the physical simulation process. To identify the optimal timing for activating acceleration strategies, we propose the PTPE model, attempting to correlate the temporal quality of current fluid rendering with frame rate and standard deviation. To fit the model, we conducted a pilot user study, gathering 16 individuals to rate rendering results under various configurations, ultimately fitting the tolerance threshold when PTP equals 4. When the tolerance is less than 0, we believe it is necessary to activate the acceleration strategy to maintain the PTP score. To demonstrate the effectiveness of our ViP-Fluid method, we conducted comparative experiments against state-of-the-art methods across 3 scenarios. Here, the traditional position-based fluids method serves as a benchmark. This presentation shows the results at a baseline of 32K coarse particles. The experimental results exhibit good rendering quality and operational efficiency. With our acceleration strategy activated, the rendering quality remains visually satisfactory, with a speed-up ratio comparable to SOTA methods, and in some cases, our method is more than twice as fast as the high-resolution PBF. To showcase the quality comparison, we displayed our method's rendering results in 3 scenarios side by side with those of high-resolution PBF under synchronized physical step length. Subsequent user studies also demonstrated the visual fidelity of our approach and user preference. In forced choice tests, our method showed significant differences compared to SOTA methods. For more information, please read the main text and the supplementary materials. Thank you for watching.